Welcome to AP Chemistry at Hononegah. Today we'll be looking at our last set of notes from Chapter 8. We'll be looking at the strength of bonds or bond enthalpy and how we can use them to calculate the enthalpy change in chemical reactions. Back in Chapter 5, we did delta H calculations using Hass's law and formation enthalpies. We can also estimate delta H's for reactions using bond enthalpies. Now, the strength of a bond is typically measured by how much energy it takes to break the bond. And that's referred to as bond enthalpy. So literally, in a Cl2 molecule, the bond enthalpy between the chlorine atoms would be how much energy it takes to break that bond. And the way they denote that we're talking about a bond enthalpy, is the symbol capital P, and then after that, in parentheses, you put the two bonds we're talking about breaking. So in this case, a Cl to Cl single bond will be written as D. Cl to Cl in parentheses. And the actual measured value is going to be 242 kilojoules per mole. And that would be a ranking of the strength of that bond. The more bond enthalpy, the larger the bond enthalpy, the stronger the bond is between the two chlorines. And scientists have calculated and measured through experimental means average bond enthalpies for a bunch of different types of common bonds. And with a relatively small table here, we can actually find the delta H of many different reactions. Now, what this table lists then is average bond enthalpies for a number of different bonds. And you'll notice they're all positive, and that's because it's endothermic to break bonds. We have to put in energy to do that. So all of these are listed as a positive value, an endothermic process. Now, if we're talking about making bonds, it'll be the same energy, but now it'll be negative rather than positive. And the reason we call them average bond enthalpies is because when we're looking at the bond energy of a C to H bond, it's in a molecule. And in a molecule, the C to H bond enthalpy actually varies slightly depending on what else is in the molecule. But the difference is very, very, very small. So there really is a little bit of uncertainty with these because it's an average of multiple values, but it's a very small difference between them. You will notice they're all given to whole numbers here, not to tenths or hundredths like we often do with formation enthalpies, and that's because they are a little bit less precise. They're the average value of the C to H in a variety of different molecules. Now, when you take a look at delta H's of reactions, there's a number of different ways to actually calculate the delta H of reactions. The way that we haven't talked about yet, because we haven't gotten into drawing Lewis dot structures until this chapter, is using Lewis dot drawings and the enthalpy of the bonds in those drawings to determine what the delta H of a reaction is. And we basically do that by taking a look at, in the reaction, what bonds were broken and how much energy is involved in that, and what bonds were formed and how much energy is involved in that. And we can use those differences in energies to calculate the delta H in the reaction. So we'd be looking at the sum of the bond enthalpies that we broke, and then we would be adding that to the sum of the bond enthalpies that we formed, which, remember, that's exothermic, so we have to make it negative. And if there was more energy involved in the making than the breaking, overall it would be exothermic, negative in value. If it took more energy to break than we got back when we made, then overall it would be endothermic, a positive value for the delta H of the reaction. So a simple way to look at this is the enthalpies of the bonds we broke plus the opposite of the enthalpies of the bonds we made. Now, how do we make, or why do we make them negative? Well, I already mentioned that a second ago. Remember, what's listed in the table is all endothermic values, the energy to break. And if we're making, it's going to be the opposite in energy. So all we really do is change the sign. So bond making is going to be exothermic, so those really should be negative. Now, if we've got a chemical reaction, like the reaction of methane, CH4, and chlorine gas, we can use the bond enthalpies of the different bonds broken and made to actually determine what the delta H of the reaction would be. And the way that would look, remember, it's all of the bonds that we are breaking, the stuff on the left. What those bonds are that were actually broken, well, we're breaking one C to H bond, and a C to H bond has an enthalpy per mole of 413 kilojoules. And since in the balanced equation we have 1 mole of CH4, that would be 413 kilojoules to break that one C to H bond in our methane. Well, in order to form the CH3Cl, we have to also break apart the chlorine gas. So we look at how much energy it takes to break the Cl to Cl bond. Now, both of those will be added together to find the total energy that we have to put into the system to break those bonds. And then on the flip side, now we have to look at the energy that's going to be released when we form bonds between carbon and chlorine and a bond between hydrogen and Cl. And really what happens is we're forming one C to Cl bond, and we're forming one H to Cl bond. If we look up their enthalpies, and then remember their exothermic values, and we're looking up the endothermic form, so we have to add them together and make them negative. And at that point, we can add together the two, and we see that it released more energy when it formed the bonds than we spent to break the bonds. So overall, this is going to be an exothermic reaction with a delta H of negative 104 kilojoules. So that's really what we're supposed to do. But honestly, there is a little bit quicker way to do it. So we're always going to start by drawing a little structure so we can actually see all of the bonds that are being broken and all the bonds that are being formed. And then instead of looking at what actually happened, it's easier just to look at the totals. Just break every bond on the left and make every bond on the right and compare those two values. And that'll give you the exact same information as if you actually broke it down and looked at, what bonds and how many were actually broken versus what bonds and how many were actually made. So basically, break them all and then make them all is a much easier way to do it. And in order to do that, you really need to see the picture so you can see the types and also the number of the different types of bonds that you're breaking and making. And don't forget the coefficients of the balanced equation play a role. So in CH4, we have 4 C to H bonds, but if the balanced equation had 4 CH4s, then we have to quadruple that. So we have a total of 16 C to H bonds. So you'll look and find out what types of bonds are being broken and what types of bonds are being formed on the two sides, and then count them up and get their totals, and you're going to multiply the enthalpy of breaking one of them by how many you actually were breaking if you broke them all. And you do the same thing on the product side. And remember, we have to make the product side negative because it's exothermic, and then we just add the two together. That's how we calculate bond enthalpies. So rather than looking at what actually was broken, it's easier to just make them all, break them all. So let's say we're looking at the reaction that we just talked about a second ago into the calculation. Based on the pictures, I can see that I have 4 C to H single bonds. And I have 1 Cl to Cl single bond. So this is basically our bond breaking energy. So we have to look at what C to H is to quadruple it, what Cl to Cl is, and then add those two together. So these are our actual values for a C to H and a Cl to Cl. And once I find the amounts, then I can total them. And to break every bond on the left side, it's going to take 1,894 kilojoules of energy. And don't forget, when you're finding out how many you're breaking, you have to take into account the coefficients. So if we had numbers here, like let's pretend that was a 2 there, that's going to double. And instead of multiplying by 4, I would end up multiplying by 8 here. So don't forget your coefficients when you're figuring out how many bonds you are breaking. And the same thing would be true when you're making the bonds. Don't forget the coefficients there. But on the product side, we're not just going to do the same thing. We have 3 C to H bonds, we have 1 C to Cl bond, and we have 1 H to Cl bond. That's what we're going to end up with on the product side. So we look up those individual bond enthalpies, multiply them by the appropriate value, and then sum them all up to find out what the total is. Now remember, this is supposed to be exothermic. We're talking about making or releasing energy when we form these bonds or make these bonds. So when we do the math, it's going to be 1894 plus the opposite of 1,998. And notice we get the exact same information. So rather than trying to figure out exactly what was broken and made, it's easier to just break them all and then make them all and compare those two energies. And it really just simplifies the process. You're going to get larger numbers, but remember, your calculator's doing all the work. Now, there is a direct relationship between the length of a bond and the number of bonds between the two atoms, and also the bond enthalpy. So looking at the average bond lengths for the different bond types, you can see that in the case of C to C, that was its bond length, 1.54 angstroms. As a double bond, it's 1.34, and as a triple bond, it's 1.20. So as the number of bonds is increasing between the two common atoms, the bond length seems to be decreasing. And that's going to be true in every situation. If you look at an O-to-O single bond versus an O-to-O double bond, the double bond is going to be shorter. And if you look at their enthalpies, it's going to be the exact opposite. They're going to increase. So overall, the energy needed to break the single bond versus the double bond versus the triple bond is going to be more and more energy. So as the number of bond increases, the bond length is going to decrease and the bond enthalpy is going to increase. Now, one of the things that we talked about before was this energy diagram. And I want to take this and use it to discuss a couple of quick things. Now, first, if we have two atoms that are infinitely far apart, their energy is going to be up here. Now, as they get closer together, if they're attracting each other to form a bond, that attraction, as they get closer and closer and closer, is going to get stronger and stronger and stronger, and our potential energy is going to drop. So it's releasing energy as that bond is forming. Now, what's happening is we also not only have attractions, which are lowering our potential energy, but we also have repulsions. Remember, we have two electron clouds that are repelling, and we have two nucleuses that are repelling. And as they get closer together, we're eventually going to reach a balance between the two. And any closer, and we're going to be at higher energy. Any farther, and we're going to be at higher energy. So this would represent our bond length for, in this case, two hydrogen atoms, because it's the energy to separate two hydrogen atoms. From here to here, that would be its bond enthalpy. And the distance from here to here, that would be its bond length. So to tie together bond length and bond enthalpy with the diagram we looked at before, that's what it would look like. Now, one of the things that I've seen before in the AP test related to this is to show a general understanding of what the graph looks like with changes in the situation. So what we're going to do is we're going to pretend, instead of H to H, that it's C to C. So let's pretend that we have a carbon-to-carbon single bond we're breaking, and this would be its bond length, and this would be its bond enthalpy. So let's pretend instead of two H's, it's two C's. And this is what the graph would look like. How would this graph change if we were looking at a double bond situation? Now remember, when we have a multiple bond, it's getting shorter, so its bond length should decrease. And the bond enthalpy is increasing, so this should get bigger. So one gets bigger, one gets smaller, and what we're going to then end up with is a situation that looks similar to what it did before, but notice the bottom is shifted farther to the left and farther down. And that's because the bond length was decreasing with the multiple bond, and the bond enthalpy was increasing. So it's going to maintain the same general shape, but where the bond length and bond enthalpy is at are going to be different in this new situation. And that finishes our fourth set of notes.